at mainnet in the coming weeks. We'll be launching as the scalability and settlement engine used by Diversify, which is a non-custodial trading DEX over Ethereum. And we hope to be servicing other exchanges as well, also expanding to the area of non-fungible tokens and gaming and things like that. We released no token. We have a funding of $40 million from 2 rounds of equity and Ethereum Foundation grant. So usually we talk about scalability, about how we can process around 10,000 trades per second on Ethereum, and as I said, that we'll be servicing non-fungible tokens, but today that's not what I'm going to be talking about. Rather, it's about how we can sort of access and work with the larger developer community, and I'll be talking specifically about 2 projects and 2 potential ways to integrate and work with code released by Starkware, and in 2 very different contexts. So I'll start with the first one, which is going to be open source code that we already have committed to deliver and will be delivering in the summer and start looking to integrate with developers in the spring. And this may interest folks both on layer 1 and layer 2 who are looking for cool projects and working with cutting edge, efficient ZKPs. So let's talk a little bit about the open source code that we're going to be delivering. So this is the Stark-friendly hash project that we've took on ourselves about 1.5 years ago, and I just want to tell you, recount the history of how we arrived at it. So in the summer of 2018, when we were a much younger and smaller company, basically the very first project that we took on ourselves was we received a very sizable and generous grant from the Ethereum Foundation. And the nature of the grant was sort of milestone dependent, and it requested us to recommend a Stark-friendly hash and to implement it in C++. And the statement we need to prove is basically a proof of a hash chain, that you took a long file and you produced its hash correctly and generate a proof for that. So the specs for what we needed to do were quite daunting at the time. We needed to be able to generate proof for a rate of more than 100 hashes per second, and this has to be done on a quad-core machine with 16 gigabytes of RAM. At the time, this looked quite hard to achieve when we took this on ourselves. The grant also states extra bonuses if we manage to hit higher targets, a rate of 1,000 hashes per second on a quad core, and even one further extra bonus if we manage to reach 10,000 hashes per second. And what we need to prove is basically that we inspected a 100K long hash chain that corresponds to roughly 3 megabytes of data, and the proof must be smaller than 200 kilobytes size, and also it must be verifiable in 10 milliseconds or less. So this was what we were asked for 1.5 years ago. What happened is that we used all of this funding that we received in order to solicit a bunch of new constructions of Stark-friendly hashes, because the list of existing hash functions wasn't quite right for it to be proven. So, standard hashes like SHA-2, SHA-3, Blake, and others, they were designed to optimize and minimize electric consumption or the speed on standard hardware, but they were not designed to minimize the time it takes to prove stuff over them. So we understood that we need new constructions, and sort of again, with this funding that we received from the Ethereum Foundation, we went ahead and funded a whole bunch of research, and also other research came along. And basically, we're now at a state where basically 4 new constructions have been suggested. The first of them was broken. That's the Jarvis Pepper one. It was the very first one. And then we have the Hades Mimsi, which is StarCAD Poseidon, already being deployed by various teams, among them O of One and Loopring, Vision Rescue, which is another family of hashes, and the GMIMSI family. So all of this happened over the course of the past 2 years, and most of it was funded from this grant. So this is what happened first. The second thing that we did is we led this process of public scrutiny of the constructions, and this included several things. First of all, we understood that the algebraic cryptanalysis of these ciphers is going to be extremely important. And indeed, the very first attacks on Jarvis and Pepper were of this nature. So we contracted the world experts on this matter, who actually sit in Paris, Professors Jean-Charles Fougère and Ludovic Perret, and we asked them to specifically target their algebraic cryptanalytic tools on these constructions, and we have received a report looking at all kinds of weaknesses and strengths of these different constructions. We also started a challenge, a public challenge that is currently running, basically where if you break the hash, you get the cash, right? There are smart contracts deployed on Ethereum that you can now access, and if you can find a pre-image for any one of these challenges that haven't been broken yet, then you can get your Ether automatically. And a bunch of the small security challenges have been broken, the 45-bit ones. To the best of my knowledge, none of the 80-bit ones have been broken, and this, of course, helps us get more confidence as to the security of these new constructions. The last thing that we did is convene a dedicated committee of symmetric cryptanalysts headed by Professor Anne Cantot, who also sits here in Paris. So this committee took place here in Paris. We attended it, a bunch of folks from Starkware. There were representatives from the Ethereum Foundation, Zach Williamsons and Dankite Feist were there. And of course, 10 symmetric cryptanalysts, you know, like the best experts in the world for this. They looked at it and they generated a report that is already publicly available. You can write to us, but we'll also soon post it on our website. And basically what this report says is that among the hashes, it sort of feels least, you know, it feels less comfortable about gMIMC for all kinds of symmetric cryptanalysis reasons. It feels slightly more confident, but still there's some doubts or question marks around Starkhead and Poseidon. So it's not like there is an attack, but there are some things that make them feel a little bit uncomfortable. And they felt most comfortable with Vision and Rescue. That I should point out that in terms of their Stark friendliness, actually Vision and Rescue are less friendly than gMIMC and Poseidon, but they are, you know, currently, to the best of our understanding, a little bit deemed a little bit safer from the point of view of their security. So what's going to come next is that during spring, which is soon starting, we'll first of all generate a final report with our recommendation, and we'll also start a code audit process because you know, you need this code to be audited by independent third parties. At that point, we'll also invite you know, various developers who want to start building on this code to start accessing it and using it and working with us or independently on it. And then summer of 2020, that's when we, you know, promise to finish this project, and we will be releasing open source code for everyone to build on under some license that the Ethereum Foundation will deem fit. I think it will likely be something like around you know, Apache or MIT, but something very, you know, usable. So now it seems likely, as we're standing now, pending, you know, further cryptanalytic, you know, scrutiny, but it seems like we'll be recommending and implementing Rescue as the Stark-friendly hash. And, you know, it's detailed, this construction is detailed in an academic paper by Abdelrahman Ali, Tomer Ashur, myself, Simon De Hooge, and Alan Shipienchak, and you can find it online. So I just want to tell you how it looks like and why is it sort of Stark-friendly. So the state, as you're generating the hash, is comprised of 12 field elements. Each field element is around 62 bits large. And the sort of way that you hash things is basically you operate in 10 rounds. And all of these rounds look the same. So let's focus in a little bit on how a round looks like. So you take your 12 field elements and you apply this transformation. You first of all take each field element and you take its cube root. The cube root is uniquely defined in this field. There's exactly one value that will give you the cube root modulo p for the p we're working with. So you took cube roots of each one of these 12 field elements. Now you get 12 new field elements. You multiply them by a fixed MDS matrix. So you get 12 new field elements and you add a round constant to this thing. So you add like a fixed vector that is sort of random looking. And then you take these 12 field elements and you cube each one of them again. So you're basically taking a cube root, doing some sort of linear mix, and then taking cubes again. And you do this 10 times, this process. So you take your output, put it in the next row, and fill it up. So in terms of what we call an algebraic execution trace, you can see that for one invocation of the hash, you get an algebraic execution trace that has sort of 12 rows in this case, and 10 columns, or 10 rounds, and a total of 120 field elements for specifying this algebraic execution trace. So now the next thing I want to tell you is that this is actually, today, the fastest prover in the world for a hash chain. So what is the statement we're discussing? The statement is, I know some file f such that z, which is the public input to the statement that everyone can see, this z equals the hash chain of f, where a hash chain of a file is computed by, I mean, you take your file and think of it as a sequence of words. Let's say each word is a 62-bit, integer that we think of as a field element. And what you do is you apply your hash sequentially to each one of these words, one after the other. Okay? Actually, a word is not 62 bits. It's actually more like 240 bits. And the kind of proof that we're doing is a ZK Stark. Actually, the code we're releasing does not have zero knowledge, but that's one of the projects that we'll be soliciting, is adding zero knowledge to it. But it is a Stark, which means it is scalable. The proving time is quasi-linear. The verifying time is exponentially smaller than the file size. It is transparent, so there's no trusted setup. And it is an argument of knowledge, meaning that seeing a proof actually convinces you that the entity providing the proof knows the file, not just that there exists some file that would give you this. Okay, so I want to, in terms of scalability, what we obtain is something that compresses a file that is roughly 3 megabytes long to a Stark proof that's going to be less than 100 kilobytes long. Now, why do we say it's the fastest prover in the world? So we just had to update these slides because just yesterday, Loopring announced a yet faster version of libsnark, or their version of a faster snark prover that actually manages to do around 160 hashes per core, which is beautiful for snarks, or around 640 hashes. The previous world record, which I believe came from the Coda project, was 30 hashes per core. So it went up by a factor 5 and now is around 160. This is for the hash function Poseidon, which is a somewhat snark-friendly with security that is, there are some question marks around the security, but it's definitely something that might be usable. What we can do for Starks is, if you take Peterson, which is provably secure under assumptions of the discrete log, we can run on something like this quad-core computer at a rate of 64 hashes per core, which is, used to be twice faster than the fastest snark, even for a snark-friendly hash. Now it's 3 times not as efficient. But for rescue, which is slightly less friendly than Poseidon, but still friendly enough, we will definitely release code that will be more than 600 hashes per core. We say more than because we're still finalizing the code. It might be somewhat higher than that, reaching a total of 2,400 hashes per second on a quad-core machine. I'm reminding you that the challenge asked us to go at least over 100 hashes per second, so we're sort of completely beyond that, and actually even above the first sort of bonus level of 1,000 hashes per second. Okay, and again, this is the fastest prover out there. Now, if you ask yourselves, why is this faster than what you can do under number theoretic constructions that also require a trusted setup, like a snark? The reason is, there's many reasons, but let me just mention 3 important ones. First of all, because we don't rely on any number theoretic assumptions, we can use any field that we like. So we actually go with fields that are supported by very fast hardware, just commodity hardware does them very efficiently. So we're going for a field that has less than 64 bits, so that multiplication is extremely fast, and you could think of it as if there's already an ASIC that is dedicated for doing this fast multiplication at 1 to 2 nanoseconds per multiplication. Second reason is that we get to choose which hash we're using in order to generate the commitments for various parts of our proof. So the way our proof works is that you commit to stuff in the proof, and then you need to reveal information based on queries. So we can use the fastest hash out there. We picked Blake 2. Maybe if Blake 3 is going to be faster someday, this is another route for improvement. And the last thing is that because we're working in a system that does not require bilinear pairings, we can basically work with any degree of constraint. So we can work with constraints of degree 3. Remember that the construction of rescue talks about cubing and cube roots, and because of that we get roughly a factor 2 efficiency over what would have happened if we would have used something like R1CS and bilinear pairings. So these are some of the reasons why the prover is faster, and again, it is the fastest prover in the world for these kinds of statements. Now, when we release the code, we'll also offer the users or developers this sort of trade-off that they can play with. So there is a parameter called the rate of the code, and you can play with it a little bit. So if you go with a baseline of a rate of 1/4, that's sort of the baseline, you get a proof that is somewhat large, around 80 kilobytes at 80 bits of security. If you want the proof size to go down, you could do that, but then your proving time goes up a little bit, so you can play this trade-off. And same thing if you go down to a rate of 1/16, your proof size will go down even further, but your proving time will go up a little bit. And same thing happens when you go to 120 bits of security. So just to summarize, the next steps are, first of all, in the summer, we will be releasing open source code for this. You could say that this is the first time that Starkware is releasing, general open source code, definitely for provers. I mean, we did release things like the Stark 101 educational code, but this will be production grade audited code that for provers and verifiers. It will go through auditing in the in the next 3-4 months. And sometime in the spring, we're planning a workshop for developers who want early access to this code and want to build on it and start using it. Again, this will be open source code at the end of the day, and we just hope and believe this will be starting point for a lot of cool projects based on this. So if this interests you, then please apply to us today. You can come up and talk to us, or send an email. At the end of the talk, I'll show you where to send your email to sign up. Now, the next thing I want to talk is a different set of developer tools that we'll be releasing even sooner. And that is what we call, not scalability, but rather snailability. So using crypto to warp time. Now, already in 1996, there was a beautiful paper by Ron Rivest, Adi Shamir, and Wagner that talked about using cryptography, in their case it was RSA, in order to create a delay in time, to have something that is the analog of a sealed envelope that automatically opens up after a fixed amount of time. And this is extremely useful for a lot of applications, things like auctions. You want a sealed bid auction where people can put the envelope and it will definitely open up without any ability to retract your bid, but no one knows what's in it until the time has lapsed. You can use it for deferred payments. Let's say you're renting an apartment, so you want to have these payments that will open up once a month, but you can't open them before, and you can't backtrack on them, and so on and so forth. More recently, the notion of a VDF, of a verifiable delay function, by Bonnet, Bunz, Bonneau, and Ben Fish, has gained a lot of popularity. It is extremely useful for proof-of-stake mechanisms, and there are a lot of chains that want to become proof-of-stake or start off as proof-of-stake. So this is sort of the analog of a roulette wheel that is spinning, and everyone knows that deterministically it will have a fixed output, but no one knows in advance what this output will be. So what I want to tell you about today is about code that we'll be releasing, basically that gives you, for the price of one Stark, you can get both applications. You can have a mechanism or a smart contract that supports both delayed randomness, as in the roulette wheel example, and it also supports a time lock, which gives you, sealed bid auctions for a whole variety of things. Vitalik was mentioning the MEVA, right, the mining extractable value. Auctions, you could use it for auctions over all kinds of DeFi contracts. And again, we'll be releasing these things, and if there are developers who want to start building on them or using them, please talk to us so we can spec them. And here I want to explain a little bit about what exactly is going on and how do we get one mechanism that gives you both things. So a good analogy to have here is that of a good old jigsaw puzzle. And there are three properties that are important to us. A jigsaw puzzle, right, if you have it all sort of already made up correctly, it's very easy to disassemble and scramble it up. It's certainly much faster than going in the other direction of fixing it up and putting all the pieces in place. So that takes more time. But once all pieces have been put in place correctly, it's very easy to verify that that's the case and to see if it's the correct puzzle being built, and there's only a unique way in which you can rebuild the puzzle. So we'll do something that is like this, but is cryptographically, and we'll use this jigsaw puzzle to get two applications. So you could still have this jigsaw puzzle example in mind, and if you have a jigsaw puzzle functionality, you can first of all get a verifiable delay function. So this analog of a roulette, something where the randomness is already deterministically baked in from the start, but no one knows what it will end up being. And how do you get that? So you take a blank square paper, you sort of draw the contours of a jigsaw puzzle, so it's completely white and blank, and now you actually mess it up, right? And after you messed it up, you take each one of these pieces and you write a random coin toss on them. And then you throw it to the world and you say, here's the randomness that I'll use, right? This will be, the way I decide who gets whatever it is, or this is the randomness, the way I'm going to elect my leader. So you wait, and it takes a lot of time for this puzzle to be constructed. Once it is constructed, everyone agrees that this is the unique, correct way for it to be constructed, and now the randomness is revealed, and no one knows much in advance what this randomness will be. But you could take the same jigsaw puzzle and reverse things and get the other functionality, which is a time lock puzzle. So you take your large blank piece of paper, and before messing it up, you write your secret, right, from left to right or whatever in some fixed way. Now you scramble it and throw it to the world. So it will still take a lot of time for it to be unscrambled and put together, and then once that is done, right, the whole world knows what was this secret that you locked in it at the start of time. But it's the same functionality that you can use to get both things. So this is what we're going to be building and releasing. So what we need is a function that has very quick disassembly, but is slow to assemble. So in mathematical terms, you want a function such that f is very fastly computable, but the inverse of f takes a lot of time to compute. And what we'll do is, you might wonder, where does the star come in here? So it comes in because we'll use it to speed things up even more, the verification. So we'll start with this thing that's in a time asymmetric encoding, something that is fast in one direction but slow in the other. And then we'll actually, okay, wrong button. So then we'll actually speed up the verification by applying a Stark to the fast direction, and this way save on the verification cost. So here's the function, there's the function that we will use for the time lock or for the, for the fast direction. It's a very simple function. Basically, you repeat many times, let's say 1 billion times, the process of taking x, cubing it, and adding some number to it, let's say 42, and you take mod p. You repeat this a billion times. It will take 1 second to compute this thing, and that's the way you lock something. And if you want to unlock it, you're going to have to run the reverse computation, which is easy to define but harder to compute, because at each step you need to subtract 42, which is easy, but then you need to take a cube root modulo p, which will take you roughly log of p many multiplications. So if you do the math, if it takes you 1 second to lock something, because let's say 1 billion steps took you that long, unlocking it will take you 2 minutes. And this is a very sequential computation. We don't know of any efficient way to make it much faster. And the analogy here is that you want your computation to be a little bit like, having babies. So one pregnant woman will have a baby after 9 months, but we don't know of a way to take 2 pregnant women and get a baby, a healthy baby in 4.5 months. So that's the kind of function that we're looking at here. If you start with 30 seconds of a time lock, it will take 1 hour to unlock. And I just want to mention that locking, for the purposes of sealed bid auctions, is a very simple computation to do, right? You can write this code that's up there, and then probably you can do it very efficiently even on your smartphone. So the locking mechanism is very efficient. And one way to verify that the solution is correct is just to go and redo the sort of naive computation of the locking, right? Going down the quick route. But if you look at the gas cost for, let's say, 1 billion multiplications, this will be roughly 1 billion gas on Ethereum. And that's far too expensive to contemplate. So if you use a Stark prover that proves to you the fast direction, now the gas cost shrinks dramatically, and it is practically in the code that we built only between 1 and 2 million gas. And if you were to run a verifier for this, it would be under 10 milliseconds to verify. So not 1 second, not 30 seconds, but only about 10 milliseconds. So here are some concrete measurements for the code that we wrote. If you're looking for a delay of 1 second, if you're looking at a delay time of 2 minutes, where locking something for it would take 1 second. The proving time on our machines, and these are big machines, 72 cores, so generating the Stark proof will take you roughly half a minute. This half a minute doesn't need to start after you finished the delay. It could start even before that. So it doesn't have to be lag time. And the proof length is going to be 40 kilobytes and around 1.5 million gas to verify. And similarly, you can see that the things scale very slowly. So if you go to 1 hour of delay, the amount of gas to verify is only 1.8 million gas. So it's still very small. And you can also batch many statements of this form and still get essentially the same gas cost for verifying all of them in one shot. Now, I just want to mention that there are potential speedups for the delay. Right? You can get it to be lower than whatever it is, 2 minutes here. So someone could spend roughly $1 million, spend 9 months, and get a multiplication that is 1 order of magnitude faster. Okay? You could also use parallelization and sort of get a faster amortized delay by solving not one cubic equation, but sort of composing several steps, 2 or 3, and finding one root for a higher degree polynomial. You can fight both of these things by changing the modulus, by using more variables than 1, and by increasing the degree. And if you combine all of these things together, it will be harder. It's not impossible to shorten the delay, but it will be much, much harder and much more expensive to significantly decrease the delay, which is sufficient for our purposes. So there are other alternatives to getting a VDF. One of them is based on RSA. That's the thing that is currently pursued by the VDF Alliance. Also, class groups is another thing that is being deployed on the Chia blockchain. The advantage of Stark is, first of all, it is the only system that is post-quantum secure. It has the smallest modulus size, which means that the difference between the hardware that we'll be using and the fastest possible hardware out there will likely be small. It's transparent, no need for a trusted setup. That's also shared with the class groups. And like class groups, it is available today. We have the code written up. The other biggest advantage is that you can use it for both things, both as a time lock and as a verifiable delay function. So to give you some examples how you can use these things in actual applications, because again, we want to solicit teams to start using them or contemplating building on them. So let's suppose you want to do a sealed bid auction, and let's work with a bidding phase of 1 minute and a time lock of 1 second and proof time of half a minute. So basically, you announce that the auction bidding phase is going to take 1 minute on your smart contract, or let's say roughly 4 blocks. Now, if I'm going to lock my bid, it takes me 1 second to compute on my smartphone. So I do that, and now I post my bid to the, it's in a sealed envelope. I post it to the blockchain. No one knows what its value is. It will take 1 minute for it to be unlocked, even by the fastest computer. Sorry, it will take 2 minutes for it to be unlocked, even by the fastest computer. So by the time my bid has been unlocked already, the bidding phase is long since closed. We have to wait till the very last bid comes in and then unlock that. So it takes us 3 minutes, right? 1 minute for the auction phase, 2 minutes for unlocking the very last bid. And then on top of that, within at most another half minute, you get the Stark proof, likely even before that. And now you know what were the things sealed inside the envelopes. And you can get one Stark proof that attests to the correctness of all of the bids that have been placed. So it's one gas cost of, let's say, 1 to 2 million gas that supports all of the bids that have been placed there. And this can be run as a service. This can be integrated into your auction system and so on and so forth, or into some DeFi protocol. Here's another application that uses VDFs for generating cards in a game in a fair way. So you want to generate your cards randomly, but without the miner having the ability to control and give you better or worse cards. So the way we're going to generate them is that a user comes in and purchases a loot box. So no one knows what's in this loot box. And now we'll take the randomness from the blockchain header, the latest blockchain header, and we'll tell that user, look, this randomness together, let's say with your user ID, will be thrown into a VDF, and the output of that will determine the kind of CryptoKitty or Gods Unchained card that you get or something like that. So no one knows the randomness for a 2-minute duration, so the miners can't really collude to give you better or worse cards. And your randomness is deterministically tied to the randomness that your cards are deterministically tied to what you threw in at the very start of time, and no one can mess with it. So there takes half a minute for the Stark proof to appear. And again, you can batch and have one proof attesting to many different randomnesses if the need be. And now you can open your loot box and be comfortable that you got your cards fairly. So as we said, there's one mechanism. Think of one smart contract that will be running, and you can apply it to both fair randomness or to auctions. And if this interests you, you should come talk to us. It's ready for deployment. You get 2 different functionalities: a delay and a time lock for one Stark. And just summarizing again, so in today's talk, I've not spoken about Stark Exchange. There are talks by Diversify, our partners in this, that will be sharing a lot of exciting details on the deployment of the scalability engine as part of the Diversify trading platform. We did talk today about 2 very different kinds of ways to interact with us as developers. One is to work with the C++ code and add functionality to it for the Stark-friendly hash that is the fastest Stark or ZKP prover out there. The other one is sort of thinking about how to use and integrate and build with the time lock / VDF that we'll be putting out there. And please come talk to us here at the conference. We'll be here throughout. You can also follow us, and you can reach out specifically by email if you want to vdf@starkware.co, or if you're interested in joining the workshop for the C++ code, to workshop@starkware.co. So thank you very much. Okay, so I'm told I have 5 minutes for Q&A. Yeah, there's someone there, I think.
There is a second.
Okay.
First, thank you for your presentation. It was really interesting. I'm going to ask you a question about VDFs. In our network, we actually really need the VDF. So we looked, and unfortunately, very unfortunately, we couldn't find any that we can use now because we can't really produce ASICs. And without ASICs, it's really, there are not so many ASIC-resistant VDFs. So I'm going to ask you actually a very, very generic question. So 10 years from now, which direction you think VDFs will take? Will there be like a perfect ASIC-resistant VDFs, or there will be everyone will buy ASICs. Maybe this ASICs will be like included in every CPU. And then another question, which is very practical. Since you have in Starks, you have ability to do pretty much all kinds of things. Can you somehow use ZK proofs or Starks to create an ASIC-resistant VDF?
Okay, so great questions. About ASIC resistance, I would like to argue that the VDF we just presented here is pretty ASIC resistant, and let me explain why, okay? On the hardware that you buy today, which runs at 4 to 5 gigahertz clock speed on whatever it is, the latest 10 nanometer technology or 14 or whatever it is, right? You already have embedded within it a pretty good ASIC for 64-bit multiplication, right? And it's one of the fastest thing that interests, AMD and Intel because everyone needs a 64-bit multiplication, right? So the VDF I described here was written, temporarily for a 256-bit modulus, but we can easily build it for a 64-bit modulus. And then if you think about it, if you want to build a much faster ASIC for 64-bit multiplication, it's not that you can't, for sure you can, but you are competing against, you're competing essentially against Intel, AMD, whoever else is out there that have a very strong interest in delivering everyone with an extremely fast, very high-grade, low nanometer kind of technology. So it's not impossible, but it would be extremely costly and time-consuming, probably, I'm guessing, tens of millions of dollars to hundreds of millions of dollars to get a factor 10 improvement, if even physics allows you that. So I would say that so the closer you go to 64-bit modulus, and if you go to, let's say, 128-bit modulus, you're still, the ability, like the amount of dollars someone would have to put in and the time it would take to get a 10x improvement on the delay time, I would say is extremely high. So to summarize, I think that the Stark construction that we presented here and which is ready for deployment is very close to ASIC resistant as much as anything can be. And to answer the second question, because of these reasons, I believe that, and I hope so, but of course I'm speaking from a very particular position, I hope that this will be the direction that all VDFs take because of the simplicity, because of the well understanding of the basic problem that we're using as the VDF. This is not class groups where research is still very preliminary. This is about just taking roots in a finite field. So I think VDFs will in the long run look like this.
Thank you.
Okay. So I'm told my time is out. Thank you very much.